Good day and welcome back to the final part of our discussion on Green's theorem. As previously mentioned, this video will cover a worksheet which you can find on Canvas or either the final page of the Green's theorem note handouts. And as usual, I would recommend that you spend some time going over these problems before viewing the rest of this video or viewing the solutions on Canvas. And in this video, I will specifically say something about problems 1 and 2, not complete solutions, but give you a very strong starting point and intuition. So for the first problem, we're asked to evaluate a line integral over a curve C, which is the boundary of the region between a circle of radius 1 and 2 with a positive orientation. And if you think all the way back to that first video on Green's theorem, we discussed such a scenario. That is, how can we give this a positive orientation? And the idea is that if we pick a starting point, doesn't matter which one, we can travel around this outside curve in that counterclockwise direction. And note, as we're traveling around it in the counterclockwise direction, we're enclosing a region to our left. But once we get to that starting point, we will travel to the inside curve, and to make sure that we keep enclosing a region to our left, as we travel around the inside curve, which would require us to go in this clockwise direction. And note, we have to go over this dashed line segment along the x-axis in both directions, which means that portion of the line integral actually cancels itself off, and we get this nice annulus region bounded by the two simple closed curves. And this is an ideal scenario for us to apply Green's theorem. In fact, I think it would be much more difficult to attempt to evaluate this as two line integrals, one over each of these curves. Green's theorem gives us the double integral over the region D, and we integrate dq dx minus dp dy. So remember, we have p dx q dy in our vector field, and we integrate dq dx minus dp dy. In this case, dq dx is 4x cubed plus 4xy squared, and dp dy is 0. And it is perfectly fine to jump immediately to this step as long as we do so correctly. Qx minus py. And let's take this one more step. The observation I want to make, and hopefully you've already made, is that this region is handled very nicely with polar coordinates. You have r values between 1 and 2, and theta values between 0 and 2 pi. So we could convert this into a polar integral. And note, when we are converting into a polar integral, it's always worth taking a moment to consider our integrand. Seeing an x cubed and an xy squared together might prompt us to try to factor out that x, or in this case really a 4x, and we would have an x squared plus y squared left over. So a bit more conveniently, we would have 4r cosine theta from the 4x. X squared plus y squared is r squared. The r values vary from 1 to 2, and the theta values vary from 0 to 2 pi. And I'll note that at this point we have a potentially very quick integral to evaluate. If you break it up into an integral over theta times an integral over r, you can ask yourself, what happens when you integrate cosine from 0 to 2 pi? But I will let you take care of those remaining details. The second problem I want to mention is number 2. Find the work done by a vector field in moving a particle from 0, 1 to 2, 0. And the phrasing of this question is a very big hint to consider a certain property. Note that the curve itself hasn't been specified. which indicates it might be conservative. So that phrasing is really a hint to think about the fundamental theorem of line integrals. So what we want to think about is for the given vector field f, the work done would be the line integral over some curve C, I guess connecting those 2 points, going from 0, 1 to 2, 0, pick your favorite one, f dot dr. If f happens to be a conservative vector field, we would use the fundamental theorem of line integrals. So pq, in terms of the components, p sub y is minus e to the minus y, q sub x is also minus e to the minus y. So we do have a conservative vector field. And the fundamental theorem of line integrals now tells us the curve itself is completely irrelevant in this scenario, that what we would get back is the potential function for the vector field evaluated at the endpoint of the curve minus a potential function f evaluated at the starting point of the curve. And I will leave it up to you to find that potential function, but once you find the potential function little f, you will be good to go. And for the given vector field big F, it should be rather quick to find that potential function. And the few usual reminders. Full solutions are posted on Canvas. Work through these, compare your work with those full solutions. And as usual, if you have questions, do not hesitate to reach out. Send me an email, stop by the virtual office hours. So stay tuned and take care.